Okay, so today we're going to be talking about lesson 3, which is about exponents and radicals. So first, we're going to go through some definitions. So an exponent is just a simpler way of describing like repeated multiplication. So it usually comes in the form of x to the y. So we have an x, and then there's a small y on top. So what it's essentially saying that it's x multiplied by itself y times. So if when we put in numbers, it will be like, yes, x to the y would be x times itself. How many times is y? So we could say like 2, yes, 2 to the power of 5 is just 2 times 2 times 2 times 2 times 2, which is 5 times. So when we look back on the general form for an exponent, the x is called the base and the y is called the power, and the whole unit in itself is called the exponent. But do note that when we are saying it in words, we don't say x exponent y or something like that. What we say is that we have x to the power of y. So we're going to go to the next topic, which is exponent rules. So this is pretty important. So the first rule we're going to go over is called product rule. So the general form for this rule is that we have a variable, for example, a base a to the product rule. So what we have is that we can have a base a to the power of y multiplied by a to the power of x. And then what this is actually equal to is a to the power of y plus x. So this is why it's called the product rule, because we're multiplying. So we could do a little example with this. So when we have something like 2 cubed, so when we say something's cubed, it means that it's to the power of 3, because a cube has 3 dimensions, I guess. That's one way to put it. Multiply by 2 squared, because that's a 2. And what we can do is that we can say that that is equal to 2 to the power of 3 plus 2, which is 5, 2 to the power of 5. And we could see that this is also true by doing it out by hand. So we have 2 cubed, which is equal to 8. And then we're multiplying that by 2 squared, which is equal to 4. And it gives 32 as well. So that's the
Yeah.
end.
So just thinking about it intuitively, you don't have to memorize this rule word by word, but if you just think about it intuitively, 2 to the power of 3 is just 2 times 2 times 2 times itself 3 times. And if we multiply it by 2 times 2 2 times, then what we get is 2 to the power of 3 plus 2. So we can just use our intuition to help us with this product rule.
Yeah, so yeah, that's a pretty good way of putting it. Yeah, so there's some limitations to this rule, which is that the base has to be the same. So if we had something like 2 squared multiplied by 3 squared multiplied by 2 squared, that wouldn't be possible with this rule because the base is different. One of them is 3 and the other is 2. So the next rule we're going to go over, it has no name, but we're just gonna call it the distributive rule. So what we do is that we have two bases, a times b, not the proper name. You should probably ask your grade 10 teacher later about it. So what we have is that for example, we could have a times b in brackets. And then what we could have is that they're both to the power of n. And then we could distribute the n over the a and b, and we end up with a times, a to the power of n times b to the power of n. So an example of this, so we can have in brackets 4 times 3 squared. So what we can do is that we could distribute it over. We have 4 squared times 3 squared, which is equal to 16 times 9.
So use this rule if the a times b is a pretty large number, because when it's a large number, we want to split it so we get two smaller numbers, and that just makes multiplication a little bit easier. However, if we don't use a distributive rule, we'll have 12 squared, which is not that big of a number, but it makes multiplication way much harder than if we were to do 16 times 9.
Okay, yeah, so we're going to explain another limitation of this rule. So note that the variables inside must be multiplied together. They can't be added. So for example, if we have something like xy plus x squared, x plus y squared, we can't use this rule on it because there's an addition sign. They're not multiplied together. However, this is solvable later on when we are doing polynomials. Yep, so the next rule we're going to go over is quotient rules. So the general format for this rule is when we have a base a to the power of m, and then, a to the power of m divided by a to the power of n. And this is actually equal to a to the power of m minus n. So it's the power on the numerator subtract the power on the denominator. So we can do an example. So we have like 2 cubed divided by 2 squared. And this is just equal to 2. And similarly to the product rule, we have another distributive rule for it. So what we can have is that we have a divided by b and then in brackets and then to the power of n, and that is equal to a to the power of n divided by b to the power of n. Yeah, so an example of this will be if we have 4 divided by 2 squared. You could simplify the fraction, but we're going to just distribute it because we can. So in the end, when we distribute it, we have 4 squared divided by 2 squared, which is 16 over 4. And just like the product law, if there's any addition or subtraction in the brackets, then you can't use the law. So the next law we're going to go over is power rules. So a general format for this one would be if we have a base a to the power of m in brackets, note the brackets, and then to the power of n, and this one's equal to a to the power of m times n. And do note that the brackets have to be there, or else what we're going to have to do is that we're going to have to actually figure out what m to the power of n is before we actually exponent the a. Yeah. So an example of this will be if we have 2 squared in brackets, and what we do is that we cube it, and we see that it has a bracket, so we can use the law, and we see it's 2 to the power of 6. 2 times 3, which is 6.
Oh, 64.
Oh. And what we can do is that we could do a simple example combining all the laws together. So we can have a to the power of m times a to the power of n in brackets. Oh, I'll put another big bracket around this. Yeah, and then multiply to b to the power of m. Okay, and then another pair of brackets and then a bigger pair of brackets. It's kind of complicated. And then to the power of n. So to solve this problem, what we can do is that we could start from the inner brackets. So we could first do the a to the power of m times a to the power of n, which is a to the power of m plus n, and then multiply by b to the power of m. And we note that the base is not the same, so we can't actually use product rule on those. But what we can do is that we can use the distributive rule to get the outside n, the power n, to the inside. So what we do is that we can have a to the power of m plus n in brackets, and then to the power of n. And then multiply by b to the power of m times n. Yeah, we can simplify it one time further. Yeah, so then what we can do is that I don't think we can use distributive on the first one.
We can, because there's a bracket.
Oh yeah, true. Okay. Yes, you can do multiply this together. And then the second plus. And that will be the simplest form of this expression. So we're going to move on to a fun thing about exponents, which is yx to the power of 0, basically any number to the power of 0 equals 1. Because when we think of exponents, we usually think of, as the definition suggests, repeated multiplication. So we might think that if a number multiplied by itself 0 times, it might be equal to 0. But we can actually prove that x to the power of 0 equals 1 by using simple patterns. So what we can do is that we could pick a random base, such as 2, and then we could start from, for example, the power of 4. So we have 2 to the power of 4. And we can calculate the value of that, which is 16. And then what we can do is that we could keep decreasing the power. So we have 2 cubed, which is 8, 2 squared, which is 4, and 2 to the power of 1, which is 2. And we can kind of see that there's a pattern going on. As we decrease an exponent, we divide the number by the base. So we just keep on dividing by 2, and when we get to 0, we divide 2 by 2, which gives us 1.
Now, something interesting to note that since not every number to the power of 0 equals 1, because 0 to the power of 0 is undefined. So this rule only applies to numbers other than 0. And also, it has to be a real number. So except x equals to 0.
Yeah, forgot to mention that.
It's fine. If we go further down this road, we can see that with negative exponents, so like 2 to the power of -1, we can just keep dividing it by 2 to get 1 over 2. So this all just brings us to our next rule, negative exponents.
Yes. So when we have a negative exponent, it actually turns into a fraction. So as we can see by the pattern above, if we just keep dividing, the fraction just keeps getting smaller and smaller. So we can try expanding that pattern a little bit above there. So we can do 2 to the power of -2. -2, which is 1 over 4. So we can see that we can actually express negative exponents in a simple formula, which is 1 divided by the base to the power of the power, but positive. So xm to the n. Yeah, m to the -n. That's the formula for a negative power. So we could do a simple example of this. So when we have something like 5 to the power of -2, we can apply the formula. We have 1 over 5 to the power of 2, and that's 1 over 25. And we could do one with a fraction. So if we have something like 10 divided by 3 in brackets to the power of -3, we can use a previous distributive rule. What we can do is that we could distribute the -3 over the values inside. So we have 10 to the power of -3 and 3 to the power of -3. So what we see is that we have 1 over 10 to the power 3 divided by 1 to the power 1 divided by 3 to the power 3. So that turns out to be, yes, 100, 1 divided by 1,000, 1 divided by 27. And we end up with 27 divided by 1,000.
And if you're confused on why these two are equal, we can multiply both sides by 27. So multiply by 27, multiply by 27, and the denominator just cancels out to be 1. And we have the numerator, that's 27 over 1,000. So that's why this number is equal to 27 over 1,000.
Yeah, another way of putting it is if we go back to the basics, and instead of actually using a big division sign between them, we just simply use a divide sign. And we remember back in school when we divide something by a fraction, we kind of flip the fraction and then multiply it instead.
Yeah, so this is also equal to 1 over 1,000 divided by 1 over 27. And so if we flip this, we get 1 over 1,000 times 27. So we also get the same answer, which is 27 over 1,000.
Yeah, so from this, we can kind of make up a simple rule for if there is a fraction to a negative exponent. So if there's a fraction inside brackets and it's all to the negative exponent, what we can do is that we could just flip the fraction. We don't have to do this long thing where we have to like figure it out. We could just assume that the teacher knows and we could just flip it like that. And that would be still equal. And using negative exponents, we could actually make up another proof for why x to the power 0 equals 1. So what we can do is that we can have, for example, the base x, which is basically any number that's not 0 or the limitations before. We can have x to the power of a. And then what we could have is that we could have another x to the power of times x to the power of negative a. And from the product rules, we know that, yeah, it's x plus negative a, which is x to the power of 0. And we also know that any negative exponent is essentially a fraction. So what we can do is that we could rewrite it as x to the power of a multiplied by 1 over x to the power of a. And we could see that we end up with x to the power of a divided by x to the power of a, which is always 1, unless x is 0.
Yeah, again, if x is 0, then we have an error because the denominator cannot be 0.
Yeah.
Okay, the next thing we're going to talk about is radicals as fractional exponents. So just as a reminder, a radical means a fraction in the form of n over m. So when we say radicals as fractional exponents, we mean that a to the power of n divided by m. In this case, a to the power of n divided by m, you can rewrite this in two ways. The first way is a to the power of n, and then we take the mth root of that. Now, this m is not a multiplying coefficient. It's the numbers of root. The second way we can write it is a to the mth root, and this whole thing to the power of n. David, do you want to do the 9 example? 9 to the 1/2.
Oh yeah, sure. So there's kind of a way to prove it. It's not as concrete as some of the other proofs. But what we can do is that we could say that 9 to the power of 1 is equal to 9 to the power of 0.5 times 9 to the power of 0.5. So we can see that there must be a number that when multiplied by itself must give us 9. And in this case, that number must be 3, which is coincidentally, or not really coincidentally, the square root of 9. And when we have 0.5, we can express it as a rational instead, which is 9 to the power of 1 divided by 2. And we can see that that kind of fits with our already defined rule of radicals. So we can rewrite this as a radical, which is the square root of 9 equal square root of 9, which equals 3. And we should go over like the parts of a radical.
Sure.
So should we use the example above?
Yeah, we can use this example.
Oh, I was talking about the radical over there.
Oh, wait, sorry, yeah. We can use this example.
Yeah, so we can identify the parts. So in this case, the m is called an index. And the a to the power of n will be the radicand. And this weird sign that almost looks like a division sign for long division is called the radical. It's not going to be really necessary for your grade 10 like school career, but it's just kind of a good thing to know in case it's on the test.
We can do an example for this.
Oh yeah, okay.
So
we could have something like 9 with a 5 or 3. Yeah, that works. So in this case, the index would be 3. And the radicand would be 9. We can try converting an exponent to a radical. So what we can do is that we can try converting. We can try converting 3 to the power of 5 divided by 2.
Sorry, 3 to the power of
Power
what?
of 5 divided by 2, 5 over 2, and we can turn that into a radical. So what we do is that we use the above expression for radicals. So we can see that the denominator will become the index. So it's a square root, the 2 outside. And 3 to the power of 5 will be inside. And
We can write this in another way, so we can have the power outside. It doesn't matter where the power goes. So like that.
yeah, it kind of depends on the situation. Sometimes it might make the equation easier if you put it on the outside. Sometimes it's just better to put it on the inside.
Yeah, it's all personal preference. You can choose
Yeah.
whatever one you prefer.
And a thing to note is that when we write a radical sign, if we do not put a number as the index, you will always assume it's the number 2. So, yep.
Yep. Then we to write it down.
Yeah, we can. And we can try converting a radical back into an exponent. So, for example, we could have the cube root of 7 to the power of 8. And we could basically reverse the steps above. We see that 3, the index, will become the denominator, and the 8 inside will become the numerator. So we have 7 to the power of 8 divided by 3. And there's a kind of a phrase to remember it, which is inside over outside. So what it's kind of referring to is essentially the power of the exponent. So in this case, the inside of the radical would be 8. So that would be over what is on the outside of the radical, which is the 3.
Yeah, so this 8 goes here, this 3 goes to the bottom. But again, it is important to realize that these two are equal. So the acronym only works when the exponent is inside the radical. If it's
Yeah.
outside the radical, then it won't work.
Yes. So what we're going to do is that we're going to move on to simplifying radicals. So we're going to actually take some skills from back when we did prime factorization and use that. So we can do a simple example of this to explain it. So we could have, for example, simplifying the radical of 50, square root of 50. So the first step will be to prime factorize the radicand. So what we do is that we prime factorize 50, which gives us 5 squared times 2. Oh, yep. And then what we do is that we can then use the product rule, if you could really think about it, because it's technically to the power of 1 divided by 2. So what we could do is that we could kind of split up the 2 and the 5. So we end up with the square root of 2 square root of 2, and then, yeah, 5 to the power of 2 times 1/2. So we can kind of think of it as square root of 2 times the square root of 5 squared. And 5 squared is just, and we can just cancel out the square and the square root, and we just kind of end up with 5 root 2.
Again, notice the difference between 5 root 2 and the 5th root of 2. In the first case, the 5 is the coefficient. So 5 multiplied by the square root of 2. In the second case, we're trying to find a number that when multiplied by itself 5 times will get the number 2. So these two are very different, and just be mindful of them.
Yeah. So simplifying radicals kind of allows us to do some things that we might have thought is not possible before. So for example, when we are adding radicals, the radicand has to be the same within the radicand, and the index has to be the same. So for example, if we have the square root of 12 plus the square root of 27. Oh, yeah, good rule to write down. And doesn't the index have to be the same as well?
Yeah, the index
Yeah.
does.
Yeah, so we have square root of 12 plus square root of 27. The radicand is not the same, so we might think it's impossible, but what we can do is that we can simplify it. So we could first simplify the square root of 12, so we prime factorize 12, which gives us 2 squared times 3. And then what we can do is that we can factorize the 27 as well. So we got plus the square root of 3 cubed. So then we could simplify. We get the square root of 2 squared. Oh yeah, 2 root 2 and 3 root 3. And we see that the radicand is the same. So what we can do is that we can just add them together. We get 5 root 3. Should we do another example?
Sure.
So we could try simplifying 3 root 27 plus 5 root 48.
Sorry, please repeat it.
3 root 27 plus 5 root 28. 48. Sorry about that.
48? Right.
Yeah, it wouldn't be possible with the 28.
Yeah.
So we could first prime factorize what is on the inside. 3 cubed, and then... Oh yeah, okay. Way faster.
Memorization.
Yes. 9 root 3 plus, which is 20 root 3. And then what we can do is that we can add them together, 29 root 3.
Yeah, so thing to notice is that we're always trying to extract the biggest even power from all the factors. So what do I mean by that? For example, when we have 3 to the power of 3 here, we try to extract 3 to the power of 2. When we have 2 to the power of 4, we try to extract 2 to the power of 4. So we're always trying to extract the biggest even power. And then after we extract it, this just becomes 9 root 3 and 20 root 3.
Yeah. A more general way of thinking it is that instead of thinking about like being like twos, taking out in twos, you would be taking out multiples of the index.
Yeah.
The largest multiple of the index. Okay. So we can move on to multiplying radicals. So multiplying radicals is kind of a different story. It doesn't have as many limitations. So remember, for adding radicals, the index and the radicand has to be the same. But when we are multiplying radicals, the index has to be the same, but the radicand doesn't. So we could do a simple example where we have the 7th root of 2. Oh, yeah. Write that down first. The 7th root of 2 multiplied to the 3 times the 7th root of 9. So what we do is that we kind of just take each part individually and multiply it together. So we first multiply the coefficients, which is 1 times 3, which is 3. And then we multiply the actual radicals. So that's the 7th root of 2 times 9, which is the 7th root of 18. And we can actually simplify this even further. Wait, no, we can't. I forgot it's the 7th root.
Yeah.
Okay. So we can do another example where we have 2 times the 7th root of 7 times 2 times the 7th root of 12. So we do multiply the coefficients again, which is 2 times 2, which is 4. And then we multiply the actual radicals, which is this 7th root of 7 times 12. Which is 84. Got that remembered.
Yep.
I think we could simplify that further.
We can.
Oh, wait. Yeah. Oh my gosh. I keep forgetting it's the 7th root.
Yeah.
Okay. Wait. Okay.
It's fine.
Well, that's kind of dumb. Oh, yeah. And there's actually a kind of a way of getting around the same index thing. So when we are multiplying radicals, if the radicand is the same, but the index is different, we could kind of cheat it by converting it into a fractional exponent and then solving that instead.
Yeah, so for this one, we won't be giving any examples because it's just the same as the as the product rule. So in this case, we have two equal radicands, or in this case base, and we have two different indexes, or in this case exponents. So we could just convert it into an exponent and then use the product rule to solve.
Yeah. So we're gonna move on to dividing radicals, and it's actually like really similar. It's almost the same as multiplying. So we kind of do the same thing where we divide the coefficients first, and then we divide the radicals. So we can do a simple example of this where we have 3 times the 4th root of 11 divided by 2 times the 4th root of 10. So we can't simplify this one that much, but we can kind of do it. So we divide the coefficients first, which is 3 divided by 2. And then we multiply that to the 4th root of 11 divided by 10. Yep. I don't think that one's too complicated. So I think we can move on. So we talked about negative exponents, and now we're going to talk about negative bases. So if we have something like negative 4 in brackets squared, what we end up with is a negative 4 times negative 4, which is positive 16. And we can also do another example where negative 4 in brackets is cubed, and that is negative 4 times negative 4 times negative 4, which is negative 64. So we can kind of see a pattern here. If the base is in brackets and it's negative, if it's to a even exponent, it's always going to be positive. And if it's a odd exponent, it's always going to be whatever sign it was, which is negative. And now a thing to worry about is that the base has to be in brackets. If we have something like negative 4 squared without the brackets, we always take BEDMAS, and which tells us to do the exponent first. So we actually first square the 4 and then add the negative onto it. So we can kind of think of it as a negative 1 times 4 squared. So we do BEDMAS, which is 4 squared, and then we multiply the negative 1. Yeah, I think that's everything.
Yeah, that's everything.
Yeah, okay.
Right, thank you for coming to our video to learn more about math. We will see you in our next lesson.
Yes, see you guys.